Get going. So we are in module 2 chapter 3 and we talk about supervised learning. In fact, chapter 3 and chapter 4 both of them talk about supervised learning. Chapter 3 talks more about econometric methods and chapter 4 is going to talk about more ML methods. So in econometric methods in chapter 3, today we'll talk about regression, and then we also talk a little bit about classification. Within regression we talk about single variable regression and then multivariate regression, and then we get into the details of single variate and multivariate regression, what this actually means, what are the advantages and disadvantages, etc., etc. And classification, we talk about logistic regression, and which is not actually a regression but it's a classification. We'll talk about it, and then that's most about this chapter. We'll see if we can finish this in a single video. Otherwise we'll take we'll do 40-45 minutes today and the rest later on. So what happens in regression is that let's talk about the single variable regression. Let's suppose you have an parameter y which is kind of related with, say, some parameter x, and then you try to mathematically model it. Let's suppose this is your x and this is your y, and let's suppose your points are distributed like this. Okay, so now you want to model a line which, let me put some points here, which models these points in such a manner that the equation of this line is as close to the real data points as possible. So that's what regression is. And once you want to put a line, you will replace this proportionality with a constant and another coefficient that gives a that is multiplied to x. So this beta naught is called as the intercept, and this is called as the coefficient of x. So what happens, let's suppose this line intersects y-axis here, so this distance is nothing but your beta naught. So that's intercept, means it's the value of y when x equals to 0. So that gives me the value of the intercept, and beta 1 is nothing but it's the delta change in y with a unit change in x. So when x changes by 1 unit, what is the delta change in y? Okay, so that's the physical interpretation of what these actually mean. And so mathematically what happens is, let's suppose you are given a set of values, set of x values and set of y values, and then if you are supposed to find out beta naught and beta 1, how do you do that? And that's what Garp may ask you to do. So beta 1 mathematically is multiplication of x i's and y i's minus n times x bar y bar divided by sigma xi square minus n times x bar square. So what you do is you multiply all the x and y values that you have been given. Let's suppose in the exam you have been given a table, and since this is a single variable expression, all you need is y and the corresponding values of x. So let's suppose you have a value of x as 5, this is 7, this has 6 and 4 and probably -3 and let's suppose 15, and then there are some values of y here. I'm not intentionally putting some values of y because you need to make sure they are kind of they lie in the same pattern of things. So what happens, xi yi is nothing but 7 5s are 35 and whatever numbers are given here, and n times you find out the average value of x, find out the average value of y, and then you multiply them with n, and in this case is 1 2 3 4 5, so n is 5. So when you do all of this, you will get some value of b. Okay, you'll get some value, and then you find out beta naught by y bar minus beta 1, which you have already found out, x bar. So if you look at this equation closely, by equals to beta naught plus beta 1 x, this is very similar to that. It says y bar, average value of y, is nothing but beta naught plus beta 1 into x bar. So this will give you the value of beta naught and beta 1, and once you find this, you will be able to estimate the values of beta naught and beta 1. So actually what happens is that at the end of the day, we are trying to find out that there has as I already said, there is an intercept, and then there is a coefficient of x, plus there is some error term. Okay, now this error term is something, because as I was telling you that if your dots are like this and your line is like this, then this is your error term, right? This is your error term. So there needs to be some error term. The error term can be a problem of the mathematical model, or it can be it can be actually some kind of a measurement error, which is generally it's a normally distributed kind of an error. But this is what single variable regression is. But not all the time, not always, the output variable y will only be proportional to a single variable. Okay, so there are times, mostly in the real world, that your output term is a function of multiple variables. So let's suppose your yield of your crop, let's suppose that's your output, it's a function of the size of the field, the availability of irrigation, the weather in that area, and the amount of fertilizers or pesticides that you put, etc., etc. So your output is not a function of a single variable, but it's a function of multiple variables. So in which case your y mathematically becomes beta naught plus, say, beta 1 into x1 plus beta 2 into x2 plus beta 3 into x3, and so on, whatever are the number of variables that you have. Now in this kind, and this is called multivariate analysis. So again, the concept is similar, but we are extending it to multiple variables, and you will find out the GARP is also mentioning in the book that there are multiple ways to find out the values of beta naught and beta 1 and so on and so forth, and there are three kinds of algorithms that are generally used to estimate the values. The one is called as least square method, one is called as maximum likelihood, and the last but not the least is called the method of moments. So we will not get into the details of what these methods are and one versus the other, because that is something I suppose we will do when we read chapter 7, so module 2 chapter 7, then we'll go. But these two are the methods that are generally used. This is rarely used, Least square is generally that, you know, you find out, so there is ordinary least square and some other forms of least square methods, but it gives me an estimation of what my predicted value is minus what it should actually be. Okay, uh, let me y hat. Okay, why it's not y bar. And then you find out the square, because you don't want to you know, you sometimes your value is going to be greater than, sometimes it's going to be less than, so you don't discriminate between the two. You it is away from your estimated by some distance, so you find the square and then you minimize this distance. Okay, so that's what the least square method is all about. Maximum likelihood is about maximizing the likelihood of y to come close to the values of y. Okay, so that's how it is. For the purpose of this chapter, I think this much is good enough, and then we'll get into the details of what of each of these methods actually are. One important thing which you should know conceptually is that these are called as linear regression, but this does not mean that the variables, which is, you know, x1 and x2 and so on, whether it is a single variable or it's a multivariable, they have to be linear in nature. So the linear in linear regression is more to do so with coefficients rather than the variables. So then this is kind of a confusing thing which you should know, and which GARP will also expect you to understand, is that, you know, there can be times when, say, y can be say 0.7, which is your beta naught plus maybe 1.3 and x square plus say 1.4, let me say x1 square, and then I say x2 plus x3, and then I can say 0.7 again, x4 probably cube root. Okay, so if you look at this equation, this is not linear, it's a kind of a quadratic equation. It has you know, linear combinations of variables, and it also has the cube roots, and it can also have log transformations, etc., whatever it is. But still we call this as a linear regression in multiple variables, because you can tomorrow you can say that I am going to say x1 square, it's going to be my x1 dash, that's my new feature. Okay, so I'm going to have a feature x1 dash, which is going to be the square of you know, x1. I'm going to say x2 dash, which is nothing but x2 and x3, and I can say x3 dash, which is nothing but the cube root of x4. So if I make these assumptions, then my y will be nothing but 0.7 plus 1.3 x1 dash plus 1.4 x2 dash plus 0.7 x3 dash. Okay, so now this looks more familiar to you. So hence it is not always true that your variables are going to be in the you know, they cannot be polynomial, or they cannot be linear combination or anything else. So that's how it is. And the next thing that you need to know probably is what are the assumptions to be considered before you apply a linear regression to a problem set. So or what are the assumptions, or you can also look at it from the point of view of what can be the potential issues. So if these assumptions are not met, you cannot apply linear regression, and in that case you can say that these are some of the potential issues with regression, whether it's a single variable or a multivariable. So let's go from the simple to the more difficult one. The first issue or problem with regression is that if you consider more variables than what actually should go, then it can wrongly predict whatever you are trying to predict, because it is going to also consider the variables that are not so dependent on the output variable. Okay, but on the other hand, if you consider variables, less variables, and if you leave some variables that are supposed to be important for your output, but you leave them, then also you need to be careful. So in both these cases, if you look, you need to have some kind of a domain knowledge which should make you consider the right set of variables. So that's the first disadvantage, because otherwise it is not going to be able to capture the dependency rightly. So you need to have that kind of a domain knowledge. The second problem or the assumption is called multicollinearity. So now what happens in real time, that you have a set of features, x1, x2, x3, so on, xn, and you want to find out the value of your output variable y. Assume that your x1 and say x3 are, they are related to each other, and they are so much related to each other that they are they're collinear, or the coefficient of collinearity is 1.0, which means that they are extremely collinear with each other. So considering both of them is going to anyway create a problem. So you can just leave apart one of them and pick up the other one. That's the simple case, but then there can be times when your x1 and x2 are near collinear. Okay, they are not exactly collinear. Let's suppose this is 0.85 or so. That's the collinearity between x1 and x2. So in such a case, if we consider both of these variables independently, then it is going to overemphasize on these two variables, because anyway x1 already contains the 85% of what x2 wants to do, and so it creates problems. So that's a problem. How do we generally deal with such issues? We don't have to know them now, but at the later point of time we will understand that okay, you can consider x1, and then instead of considering x2 you can only do x2 minus x1, because that's the delta difference, or x2 upon x1. So or you do some kind of log transformations of both of them so that they don't become so collinear with each other. So that's the problem, or that's the second part, multicollinearity. Third one is the third problem, or the third assumption that you should know, is that outliers needs to be removed. So having outliers in your data creates a lot of issues. So let's suppose this is your linear regression, and these are your variables, or sorry, these are your data points, and you create this as a linear regression. But if there is an outlier here, then your line will go like this. Okay, because this guy is going to pull this towards this side. So having an outlier in your data can create a lot of problems. So you should not have outliers, which is true with most of your algorithms, but in linear regression also this is important. you should not have an outlier, and if you do, you should probably deal with the outliers first before you start modeling into a linear regression. The fourth assumption, which is the most important and being most asked, it's called as heteroscedasticity. Okay, so you will hear about this term a lot often, even if you go out for, say, interviews, and a lot of people will, it's a favorite term to be asked by a lot of interviewers, etc. So what heteroscedasticity, and then there is a term called as homoscedasticity, which is just the opposite of heteroscedasticity. What this means is, let's suppose there is a error term, it can be ordinary, least square, or it can be any other term. So there is an assumption that if, let's suppose, this is your zero error, this is your positive and this is your negative, and these are the values of, these are the values of let's suppose x or x or whatever, x1. So the ideal case is that there is zero error, but that never happens. So your error terms will be like this, okay, on either side of 0. So till the time your terms are, say, normally distributed to each other, it's okay, so your average of the error terms needs to be 0, and they needs to be equidistant from each other. The errors on each side needs to be balanced. But in case of heteroscedasticity, it means that as the value of your xi or any dependent value increases, your error terms also start showing more variance. Okay, so if you look at this, as the value of x increases, your variance or your distribution of errors also become more and more wider. Can this happen in a real life scenario? Absolutely yes. That's why this is so important. Let's suppose you're talking about stock price. So as the value of the stock price increases, there are, most of the times, the fluctuations also become more and more wider. Okay, how do you deal with this? There are means and ways. We don't have to talk all of them now, but one of them can be to take the logarithmics of the value, and then you can find out that many a times the heteroscedasticity will go away. So that's another reading of the assumptions or the problems with regular multivariate and single variable regression. The last reading on regression, it's called the stepwise regression procedure. In which case, and this is also something that can be asked, so what you do is, so theoretically you can have two methods so what is the core philosophy of stepwise procedure is that when you decide that you have a set of features x1, x2 and say xn, and you need to find out that how many of these features needs to be taken in your final equation or final model. So you can do two options. One is called the forward procedure and one is called the backward procedure. So first of all, you need to find out all the so let's suppose x1 and x2 and xn are your features, and then you do some kind of feature engineering, and then you say, in addition to all of this, I also have, say, x1 squares, Then I can also have log transformations based on the domain of the problem and what you think can be all the possibilities. So you find out all these options, and let's suppose the final list is already there. Let's call them that all predictors. Okay, so these are all your predictors that can be relevant for your problem to be solved. In the forward procedure, you start with 0 predictors. In the backward procedure, you start with all predictors. In the forward pass, you slowly started adding predictors. And in the backward pass, you slowly start removing predictors. Okay, so you try with all the permutations and combinations of all these predictors by addition here and subtraction here, and on each of these steps you calculate a matrix called as AIC, which is kind of an error metric for regression, and it will give you some kind of an accuracy to deal with the final variable that it tries to predict. By also, it is also going to penalize more predictors. So if you reach a say accuracy of A here, and all the more additions is not going to actually give you the it's not going to actually increase the accuracy, but AIC is going to probably penalize it, because adding more making the model bigger and heavier is not helping you to give you better accuracy. So it will become A plus something or A plus plus. So that, which means that this is the most optimized place, and these are the predictors that you should take in the final model. And similarly for the backward procedure also, but they are like ways to reach the same destination. One is by taking no predictors in the beginning, and the second one is by taking all the predictors in the beginning. So that brings us to the end of regression at large. The next reading that we will do is logistic regression. So while logistic regression is called regression, but it is a classification algorithm. So in case of logistic regression, what we do is that we use the same philosophy, that all the multiple variables or the features that we are trying to model, we bring them together. But since this is more of a classification rather than a regression, we have to put them through some of the kind of a function, which instead of giving the total value in say 0 to infinity, or say minus infinity to plus infinity, we have to put this in a range of say 0 and 1. So if it is a kind of a classification between two classes, let's say class 0 and class 1, this function, which we call as an activation function, this function allows us to converge all the values from say minus infinity to infinity between 0 and 1, and we come up with a graph like this, a kind of an S curve, and then we find a value threshold t, and we say that okay, if so this is your x and this is your y. So if the value is below this threshold, then this is class say 0 and this is class 1. So that's the philosophy of a logistic regression. The choice of activation function is very important. Most of the times the activation function that we use is 1 upon 1 plus e raised to the power of minus y. This means that and this is all why, that my logistic regression eventually will become 1 plus e raised to the power of, say, beta naught plus beta 1 x1 plus beta 2 x2 and so on and so forth. Okay, so that's how the logistic regression is, and it is going to become, it is going to solve the problem of classification rather than the problem of regression. So this is good enough for you to understand, because the GARP is not going to ask you to solve numericals around it. And E is for all those people who don't come from a mathematical background. E is the base of natural log. Okay, so when if you are familiar with math, you have seen a ln of, say, number x, which is a natural log for number x, and that's natural log means that e to the power of y is equals to x, or y is the natural log of x, and the value of e is 2.7 something. Okay, so that's how it is. But there can be scenarios when there is more than one class. Okay, so what happens when there is more than one class? So in the above example, we saw that we create an S curve, and then you found out the value of t threshold. If it is less than t, then it is class 0, and if it is more than t, it is class 1. So if there is more than one class, which is called as a multi-class classification, there can be multiple things that we can do in such kind of a scenario. One is called as so there are two variants of logistic regression. One is called as a discrete choice model. Okay, in this case, what we do is we do one versus all. So let's suppose there is a class 1, class 2 and class 3. So we need to create multiple models where, the first one is whether it is class 1 or it is not class 1, which means that it can be class 2 or class 3. And then we say whether it is class 2 or not class 2. And then we say whether it is class 3 or not class 3. And then we try to find out the relative probabilities of all of these three, and then you pick up the one which has the highest probability. So this is one method of finding out or using logistic regression when there are more than one class present. And this method is going to help you when your classes are independent of each other. When I say independent of each other, it means that they don't have an order. Okay, so in our first few readings we were talking about the natural orderings, or if there is some kind of pattern between the ordering or not ordering. So when the classes are fairly independent of each other, this kind of a method will work. When the classes are in order, we use something called as a ordered logistic regression. Okay, in which case you just have to know this conceptually. You don't have to get into any depth. There will be probably 1 or 2 paragraphs written about all of this in the GARP readings, but in such a scenario, in your and this ordered pair means, let's suppose you want to find out the ratings of your derivatives, like whether it is a AAA, whether it is a triple B, or those kinds of categories which have an ordered pair, that this is better than this, and then if there is let's suppose B, B's or C or whatever it is, that is there is a pair. So you find out the interim thresholds, and then you find out that okay, these are my 3 thresholds, and based on wherever it lies between these 2 regions, that will give me whether it is class 1 and this is class 2, this is class 3 and this is class 4, because these are ordered pairs. Okay, there is the last section of this chapter, and then we can move on to the next chapter, is also a classification method which is called as LDA. Okay, and there is another, that LDA is also in this acronym is also used in the NLP side of things, which we can talk later, but this LDA is more to do so with a basic classification algorithm, which is nothing called as a linear discriminant analysis. Okay, I will briefly talk about it. I don't want to get into the details of it, because for all of those who are not from a math background, may find it slightly complex to understand, and it is not worthwhile to get into the deeper mathematics of it, because we will keep talking about more and more algorithms as we shuttle across module 2. And if we get into the details of all of these algorithms or derivations of all of these algorithms, it will only confuse you, and the intent of GARP is not to ask you to solve numericals of all of these algorithms, but the intent is to look at your application side of things. When you really apply these algorithms or these methods to solve a real life problem, and they'll give you a scenario, how does it really, in what scenario you should apply which algorithm, and what kind of biases can be there if you apply some kind of an algorithm. So that's the intent. That's why getting into the math of doing things is not so important. But let me still tell you that the linear discriminant analysis, it has it has a discriminant function delta. Let's suppose it's a delta j, and the discriminant function delta j means that j is your classes. So j can be, let's suppose, 1 to the number of classes it can, let's suppose g. So there are g different categories of classes that your variable can have. These are the categories of output classes. So delta j of x is going to be, so it is a slightly complex thing, x transform sigma minus 1 mu j cap minus 1 by 2 mu of j, and we take a transformation of this, and this is also plus log of pi j cap. So this is a very complex equation. That's why I don't want you to go beyond just looking at this equation and saying this is how a linear discriminant analysis happens. X, of course, is the feature vector, so this is easy. So feature vector are those, x1, x2, x3. So this is a vector of all of those things. Mu j is the vector containing the means of predictors. Okay, so this is the vector containing the means of the predictors. Okay, and this thing, this particular symbol that you see on the top is the inverse of your matrix. In your linear algebra, this is called the inverse of the matrix. So this is going to find you the inverse of the data covariance matrix. Pi j is nothing but the prior probability of class j. Okay, so what happens, let's suppose if in a particular scenarios, by the historical evidences, if let's suppose 30% is your class 1, your 40% is class 2, and 20% is class 3, and 10% is class 4, then your pi j can take the values of like 0.3, 0.4, 0.2 and 0.1. If this is not known earlier, then we can just take them as 1 upon n, all of them as like that. Okay, so that's the pi j. T stands for the transformation of your matrices, and that's how LDF works. Okay, so don't get scared with this equation, because nobody is going to ask you to solve this equation. Maybe if they become, if they want to make this more difficult, they'll just say that, okay, what is the formula? They'll give you 4 options, whether this is this or this is not this. So that brings us to the end of this chapter. There are some appendices at the end of this chapter that you can read on your own. There are more variants of these algorithms, like your Fisher discriminant analysis, etc., etc. You get into problems with respect to understanding those algorithms. You can comment here or ping me or email me. My email is praval@gmail.com, and I will try to respond to that. But I think in your first pass of your reading, don't get bothered by getting into these mathematical things so much. Maybe in your second pass, third pass, you can get, as you get the hold of most of these things, then we can get into more details. Okay. We will start with the next chapter in the next video, which is also supervised learning, machine learning, but it is going to talk more about your, say, decision trees, and then we'll talk about support vector machines and ensemble methods, and that will bring us to the end of supervised learning. Thank you.